Hey everybody, I'm Schuyler. Hi. Thank you. All right. In previous years, I have gone through a lot of slides with a little bit of comedy. This year might wind up being more boring because we're talking about the internals of a lot of different locks over the course of several thousand years. Haha. But this is my how to make a lock talk, and the one thing that I really want to say before we dive into this, in the hopes of preempting future YouTube comments, the examples that I am using are not always entirely accurate. What we're going to do in this talk is bring you through reasons for different functions of different locks, the cause and effect, but not every cause is the actual cause for every single effect. So, know right now that I know that not every one of these examples is dead on historically accurate. Thank you, YouTube. Enjoy the talk. Okay, so how to make a lock. You have a couple of different paths. We're going to start off with the Roman locks. So, the Roman lock was pretty simple. The bar of metal that you see moving through the plank of wood and into the bolting mechanism is just a big iron bar with a bend in it. Needs to be exactly long enough in order to seat itself inside of the serrations, and then you just crank it over, and it pulls the bolt out of the lock. Pretty dead simple. So these keys, of course, are incredibly unwieldy. They're enormous, so we start making simpler keys. The simpler keys are super easy to duplicate. In particular, flat keys with no shape to them are very easy to just imitate with any flat piece of whatever. So we start to introduce something called warding. The warding will match the shape of this key. We'll look at some other warding in a little bit here, but the basic idea is that the key is the negative image of plates that are found inside of the lock. So the key is still acting directly on the bolt, and that's very important for what else we're going to be looking at here. Additionally, the flat keys are really easy to duplicate, even if they have the warding built up onto them, so we start seeing our first key profiles, where the shape of the keyway and the shape of the key have to now match one another. It's no longer just a hole in a piece of wood. But those, of course, are better together. So we have profiles, we have warding, starting to go a nice long way. However, there is something called skeleton keys. Now, all of you picture a skeleton key in your mind. Most of you are wrong. That's not a skeleton key. So, beautiful, ornate Victorian keys are just warded keys. They're made to match the wardings inside of the lock. The skeleton key is the skeletonized version of this key. So in this case, we don't need all of that metal in order to avoid all of the wards in the lock. Instead, we could just have a skeleton key that is a single post up the middle. And that would still avoid all of the wards, but it would also interact with the bolt. So a skeleton key is actually a lock-picking tool. It is the skeletonized version of a warded key, and you would have several of them. You would go in and you would try them in a series of locks, and hopefully they would open up for you. So one of the ways in which we attempt to defeat skeleton keys is via pericentric warding. So this is very elaborate warding that crosses over the center line of both sides as much as possible in order to make it very difficult to create an effective skeleton key for this system. Elaborate warding, however, requires precision. So when we just had our stick with the hole or we had our flat key, we could potentially get away with the alignment of that key being a little bit off. However, the more elaborate our warding becomes, we start to need posts for the key to be inserted onto. What we're looking at here is the side of what is called a box of wards. The wards are very simple, but it has a post right in the middle, and our key would have a hole in its post, and it would fit onto there, and that way everything would align itself properly. However, why not pattern those as well to make it even more difficult for somebody to fit a blank onto there? So we start patterning the posts. But even with the patterned posts and the pericentric warding and whatnot, I can still get wires in there at the very least. I can still get some, somewhat flexible but hard thing in there to attack the lock. So they invented the curtain. And the curtain actually ends up being really important for lever locks as well, which we'll get to in a little bit. But the curtain covers your key, and then as you turn the key, it continues to cover the keyway. So that if you're getting in there with a wire, as you begin turning the wire, that whole thing will turn with you, whatever tools you're trying to use, and it just closes off important parts of the keyway from you. Curtains became much more elaborate with the lever locks and much more effective as well. However, this entire concept is doomed to fail. The reason that it's doomed to fail is because of something called the wax pad attack. So imagine yourself a warded lock again. The easiest way to figure out the right key for a warded lock is to just take a flat piece of metal, cover it in wax, insert the wax into the lock, turn, and wherever the wax is cut away is where the wards are inside the lock. Doesn't matter if you have the curtain, doesn't matter if you have super elaborate warding, doesn't matter if you have a keyway, so on and so forth. Eventually somebody's going to be able to impression your lock. So the entire concept is doomed until this guy Robert Barron rolls in and he says, check out this cool lock I've come up with. Now, this is the first lever lock, and it's doing a couple of interesting things. Most importantly, though, this leaf spring is notched into the bolt, and there is a small lever behind this. Previously, the key has always acted directly on the bolt. Now, the key still will act directly on the bolt, but it is also going to have to lift that lever against the spring. The two notches that you see in the bolt are revolutionary. This is an amazing inflection point in the history of security. And I have a Barron-style lever lock back at the village if you want to play with one tomorrow. The basic idea is that by lifting this lever, you are freeing this notch so that it can slide out. So you lift the lever, the key operates on the bolt, sliding it out. The little protrusion drops back down into the next notch, and it's locked again. And that's dead simple, but his idea was, if I add this active element, it's going to be very difficult for somebody to get an impression of the lock. Now, this would often still be paired with a box of wards, but it would also be lifting this active element. All right, so that's all well and good, but a single acting, which is now what we call this type of tumbler mechanism, is terrible. Because you could just lift that lever up as high as you wanted and then manipulate the bolt back and forth. There was no upper limit on it, so you weren't lifting it up to the right height, you were just lifting it up. So we then get enclosed bolts, enclosed tumblers, where you can lift it up only so high, at which point it cuts you off. So that's cool, except that this now becomes incredibly easy to impression again. Because as soon as your key stops, remove a little material from it. See if it goes far enough, not far enough, remove a little material from it, and eventually you won't be lifting the lever up too high anymore, and the lever itself has told you exactly where the key needs to be cut to. All right, so next up we finally have our double acting lever tumbler. The way that this works is that the protrusion from the bolt or from the piece laying over the bolt rides inside, completely encapsulated, this channel. When you lift it to exactly the right height, it can travel across to the other side. If you lift it too high, it'll be trapped down here. If you lift it too low, it'll be trapped up here. So this is double acting. You can't lift it completely high, you can't leave it completely low, and this, again, is a revolutionary moment in the history of physical security. But everybody wants a different form factor, and we're going to keep coming back to form factor as we look at all the different locks. So they wanted to mix this up, put it in padlocks, put it in other sorts of smaller, compact forms, so we wind up with edge gates. So now we have pivoting levers that pivot from here, and instead of encapsulating the post that needs to fall into them, instead it sits right in front of them, and we have little gates in each of the tumblers. Additionally, somebody finally got around to adding more than one of these, and that's a huge improvement. So, let's talk about the tentative method. How many of you know how to pick a lock? Decent number of you? I've seen a decent number of you. Excellent. The whole idea behind picking a lock is that we apply pressure to the system. Whatever it is that's going to interact with the tumblers, in this case our post, we want to press that right up against our tumblers. When we do that, when we grind two pieces together, we can then go in and start manipulating the tumblers. or manipulating the pin tumblers in our pin tumbler lock, lever tumblers in this. And we can feel the relationship between the tumblers and whatever it is they're blocking. That was created probably in the late 1700s. It was called the tentative method at the time. I'm trying to bring that back, so please spread the word. And the tentative method works across any lock that takes a key. In one way or another, you can put pressure on the system and then feel out the relationship between the tumblers and whatever it is the tumblers are blocking. So the tentative method is going to come up a bunch, and it definitely came up with the lever locks. So one of the things they try to do is add serrations to the lever tumblers, so that now as you're pressing the tumblers into the post will catch on these serrations, and it'll be much harder to feel where the true gate is. Now that doesn't completely defeat us, but it does buy everybody a little bit of time. Additionally, we see our first detector locks, where we will know whether or not the lock has been attempted to be opened, and it will lock the person out from making any additional attempts. In this case, if you lift the tumbler too high, not only won't it turn because we have our H-shaped interior of the tumblers, but it will also trip a spring on the top of the lock, which will fire a small bolt that locks all of the tumblers down into place and can't be moved anymore. The user would have a different key to unset the detector, but you, as the attacker, would have no more means to access the lock. So then we kind of get away from the evolution of things because Joseph Brahma showed up out of nowhere with a message from the future about his crazy Brahma safety lock. The way that this thing works is that the key, which you see on the left there, has a series of slots cut out of it. The length of the slot corresponds directly to the length of the sliders, which you see at all even depths on the left, and then with the key inserted, all of the sliders will be depressed different amounts by the key. There's a gate in the sliders that correspond to the depth that the key is going to push them to, and then that metal ring in the middle, it allows them all to spin through. Brahma was probably 100 years ahead of his time. There are a lot of people that say that he was looking at what was then called the Egyptian lock, and he drew inspiration from that. But this lock came out in the 1770s, and the first European reports of the Turkish and Egyptian locks didn't happen until the 1790 whatevers, so I highly doubt that. Screw you, everybody on YouTube. Okay. But it turns out the tentative method works on this too, because if you can start rotating the plug, which contains all of the sliders, you can then feel as the sliders are grinding down and those gates are catching on the metal ring. So somebody actually manages to pick his lock not long after it's out on the market. So what does he do? He goes right back to the serrations again. Serrations are going to come up quite a bit as well. Honestly, though, the serrations for him did the job for more than 70 years. This was good enough for more than 70 years. All right. So we're going to look at the form factor again. Lever locks in this time, in the early days of lever locks, were always fitted to a door. There wasn't a lot of standardization yet. Brahma brought in a lot of standardization, but nowadays you can find lever locks in myriad and ever tinier forms. This is a phenomenal compact lever lock from Ingersoll. It looks sort of like a double-sided wafer key, and it manages to pivot a series of levers through the middle, which you can see laying out here. And it's a devil to pick, and it's fantastic. But we also just love adding more tumblers to everything. So go to Fichet 450, and now we have a four-sided lever lock, pivoting levers across all of these points and on the back side of that as well. The big problem with the Fichet was that because they made this I-beam looking key, there was a forcing issue. Because if you had a blank, that's a really strong blank, and you can just torque it out. But let's have a look at the Mesopotamian lock evolution now. Lever locks, especially the last two that I showed you, are still in use to this day. You can find them on safe deposit boxes here in America. We don't have a ton of them in the States, but you can find a ton of them off in Europe. So the first Mesopotamian locks were these door seals. The way that the door seal worked is that you had a bolt that went through the door, and then you put a bunch of clay on the bolt. And you inscribed some cool stuff in the clay so that if anybody ever entered it, you would know that they had to smash your clay in order to remove the bolt. But then somebody got the cool idea of putting some pins inside the bolt. So the original pin tumbler lock was actually just a bolt with a few holes milled out of it and a couple of pins dropped through. Right in the staple of the door, where you were sliding your bolt into, it would lock down, and you would have to use this key with a couple of pegs on it, not really all that dissimilar to the key that you have today, to lift the pins out of position and drag the bolt out. So, turns out that's really easy to duplicate when everything is spaced exactly the same all over the place, so they introduced the concept of variable spacing. They're making all of these things by hand anyway. Why not drill some odd patterns, set them off in different directions, separate them by less than equidistant distances? As long as you have the key, you're fine to figure it out. Convenience-wise, having the lock in the bolt, it was difficult to get the key into. You had to make the wacky-shaped key. There are all sorts of other reasons that it became really nice to actually have a separate mechanism from the bolt. Now, the separate mechanism from the bolt worked by having, very similar to Brahma's sliders, hence why people say that this is like this, you would have these sliders with a gap cut out of them. When they were at rest, they would be sitting down into the bolt, but there would be a channel clear for your key to go in. Your key would have a couple of protrusions that were just tall enough to lift that up out of the bolt, and then you could pull the bolt out. Then this was rediscovered by the Europeans. It was rediscovered in the late 1700s. First, this guy Towne went and did his survey of the Ottoman Empire, and this is what he said about the Turkish locks that he was finding that were exactly the same as the ones we were just looking at. This idea might be improved on, but the Turks never think of improving. Seems like a dick. This other guy is also kind of a dick. This is Vivant Denon. I've talked a lot about him here before. He was traveling with Napoleon in Egypt when Napoleon invaded Egypt, and he managed to see an inscription of a lock very similar to the ones that he was seeing all around him and the ones described by Eton. He saw the inscription, he journaled about it, and then when his journals were published in English in the early 1800s, 1803, 04, people got super excited about Egypt and super excited about the pin tumbler lock. So, again, the form factor of the Turkish lock is massive. So very quickly we see people taking that sliding method of the bolt and instead attempting to play with rotation, play with sliding but only offsetting it a very much to trip a latch. Abraham Ogre Stansbury had the first patent, and his was this big sort of rotating panel. Linus Yale Sr. had a ton of awesome patents, and Linus Yale Jr. is the guy that made the lock that you guys are using today, for the most part. What Jr. realized, more than anything, was that the long history of building a lock and then fitting that lock to a door, that the lock had to somehow conform to the specific purpose, was awful. So while the Mesopotamians, Egyptians, Turks realized that that separating out the bolt from the locking mechanism, putting the locking mechanism elsewhere but still letting it play directly on the bolt, was cool, what Linus Yale Jr. realized was that if we separate the lockout entirely from the bolt, the key is no longer acting directly on the bolt, the key is acting only on the locks, and we can take these locks, manufacture them en masse, and we'll leave it up to the door people to figure out how to get them in their doors. So he created this massive standardization. He wasn't the first person standardizing, but his took over the world. So this is how we got to the form factor that we have now. Now, one of the last big improvements in the lock that's on your door is in the late 1800s, we got what were at the time called corrugated keys. These were keys that had any sort of shape to them whatsoever. This will eventually become warded keys that have more elaborate profiles. Just this way, it's harder to get into the lock itself. But the tentative method will never be stopped, and so people try to throw a bunch of other things at the tentative method. Even with a slightly shaped key, you can still get tools in there, you can still carry out all of the normal attacks. So they try to create this paracentric warding. Yale actually, I believe, was one of the pioneers of the paracentric warding as well. Again, pericentric means that we're crossing over the center line. It makes it very difficult to get any tools into the lock, but people just make better tools. They also tried security pins, serrations, just like we saw in every other lock that we've ever looked at. And of course, they also tried trap pins, very similar to the detector, only in most pin tumbler locks, trap pinning systems where if you haven't used the key, some other pin will descend into the plug, trapping it at 10 or 15 degrees, will cease operation completely. For the most part, you have to destroy the pin tumbler version of trap pin locks. But again, we saw this with the lever locks as well. None of this works against the tentative method, ever. All right, so this is the big idea. Any lock that provides access to the tumblers can be picked. Cool. So let's not give any access to the tumblers. This is Linus Yale Sr. in 1854 on the left, and he's devised a key, which you'll actually see in the top left, that little bean-shaped thing with the little holes in it. That's actually the key. The key would be inserted into the lock, and then a panel turned without you touching the key. The key would travel to where the tumblers were. It would act on the tumblers. The bolt would be thrown open, and then the key would be returned to you. Like a bad quarter moving through a vending machine, it would pop right out again. That's awesome. Many of you may have recently seen the Forever Lock, as it's being called, which is a bike lock that performs the same function. And that's awesome. And a lot of you have been tweeting to me and emailing me and saying, check out this crazy thing, how crazy. But they had it in the early 1840s. They were doing this stuff. And a great locksmithing friend of mine let me know that they are currently called Lafayette locks, and there are still some of these awesome door lock versions of this technology still out there in the world. So keep an eye out. I don't have a great explanation of how you would attack this, actually. I think this is super cool. It's just generally really hard to use and potentially prone to error and difficult to repair. None of that means that it isn't super awesome, and none of it means that the form factor that they figured out for the Forever Lock isn't super clever. I actually think they did a really cool job. Okay. So, again, to attempt to combat the tentative method, people are like, well, okay, you can tentative method your way into our normal pin tumbler lock, but what if we start adding some like secondary and tertiary locking mechanisms in there? Now, right off, the very first thing that everybody thinks of is, let's add more. So, hey, second row of pins. But don't worry, we can totally pick that. It's fine. What about even more pins? So this, once again, is Linus Yale Sr. A lot of credit goes to Junior, but Senior was doing some crazy stuff. So the first pin tumbler, well, the first like functional pin tumbler lock made in America was actually cruciform. It came in at all four sides. The inline pin tumbler was like a couple decades later. So add even more pins, have it coming in from four sides instead of just 2 rows. Awesome, we can still pick it. But what if you added the most pins you possibly could? So the Kaba Lock Company are obsessed with just adding as many pins to locks as they possibly can. They got an early start on it by doing reversible keys with a couple of different pin chambers. Then they're like, oh, cool, 2 pin chambers was cool, but then Sergeant Queso came out. Sergeant Queso were like, oh, hey, that's cool, your 2 pins, but check it out. We have 3 rows of pins acting on 3 surfaces of our key. What? So Queso bought them. And then Queso released the Quattro. You can guess how many pins are in that. How about the Penta? And then this is the Star. They went away from the traditional. But this thing is just loaded with so many pins, and it's in such a tiny form factor. This gets the like big more and big form factor designation more than anything else. Their machining tolerances are ridiculous. Anyway, Kaba's pretty cool. Okay, but as Sergeant Queso will tell you, no matter how many pins you have, it's still relatively easy to duplicate your key. Potentially, even when they're dimple keys, to reproduce them from a visual or a photographic inspection. So Queso, much like those early Egyptians, Mesopotamians, Turks, realized that they could have variable pin spacing. So when you look at a Queso key, not every pin will be perfectly even. They have a ton of chambers, but not every chamber is filled, literally. Additionally, and this is a little bit silly and not so much in the grand tradition of security engineering, but there are a decent number of lock companies out there where when you look at their key, it looks like something amazing is happening inside of their lock. But really, a lot of the key isn't doing anything at all. So that's it, yeah. That's just the intimidation factor. All right, so let's keep going with the secondary mechanism. What if our pins could rotate? So we have medical locks, of course. Most of you probably heard of medical locks. The way that these work is pretty straightforward. If you look at the key that is coming into the top of the cylinder from the right there, instead of being cut straight across, the cuts in the key are at angles. The pins inside of the lock, you can see a small illustration of in the lower right-hand corner, the pins come to a chisel tip. Because the pins are at a chisel tip and the keys are cut to angles, as the key enters the lock, the chisel tip will orient itself according to the cuts. As they do that, there's a big bar of metal that we're seeing right here, and that bar of metal has a series of teeth on it. Those teeth will fit perfectly into slots cut into the pin. The pins need to be rotated so that the slots can be married into them from the sidebar. So that's pretty cool. But we always want a new form factor. So Medico wanted to do some cam locks, and everything that's going on there is pretty tight, relatively large, but they came up with their driverless cam lock, and this is a brilliant lock for a number of reasons. Number one, there are no drivers, hence the driverless. There are only key pins. Key pins are the pins that touch your keys. Typically, pin tumbler locks will have both key pins and driver pins, which sit above the key pins, blocking you from doing any rotation. You interact with the key pins, but you're manipulating the driver pins, blah, blah, blah. So instead, it has a bunch of chisel-tipped key pins that have holes cut into the side of them. Those holes will match into pegs in the sidebar, and even though the key pins are super small, you can still get a good distance on the holes. So they're all the same height, but just the position of the holes are different. So they're lifted and rotated, and the sidebar legs can drop into them, and it's a super precise system and very hard to pick and really cool. But what if we want to master key it? Okay, so now they came up with a master keying method for this, where you can have multiple holes on a pin, or if they're relatively near each other, you can actually tunnel out a chunk of the pin that the pegs in the sidebar can hit. So now you have multiple keys that can work in the same lock. But it turns out that Medico's original idea of the sidebar mechanism coming in is prone to an interesting feature of the tentative method. The whole reason the tentative method works are because there are all sorts of tiny manufacturing differences within the lock. In the case of pin tumbler locks, you often have differently shaped pins, pin chambers that aren't in perfect alignment, maybe something's a little ovoid or whatever. There's just everything's a tiny bit off, and when you're picking, you take advantage of all of those small differences. Turns out that the shear line between the key pins and the driver pins in the normal Medico locks and the sidebar that comes in at the locks and the rotation, they're far enough off of one another when they're made that if you apply pressure in one direction, you'll bind just the pins first, and you can deal with the shear line. In the other direction, you'll bind that sidebar, and you can deal with rotation first. Now, this is still super difficult to pick. It is not an easy lock to pick. It's still a high-security lock, but you can compartmentalize your attack. Do one thing at a time, tackle one problem at a time. Enter one of my favorite locks in the world, the M-Heart Interlocking. If we look over at the pin stacks on the right, they're a little bit out of position from where they would be finally, but look at that furthest pin. The key pin and the driver pin are actually dovetail joined to one another. They're connected to each other. Now, these also have chisel tips, and the keys are also cut to angles. When the key is fully inserted into the lock, the pins can rotate far enough that all of the joints are facing outward, and they'll all be sitting at the shear line. The plug has channels cut into it that the bottom of the driver pins can rest in, so they stay in alignment, so they can be recoupled when you turn it back around to the locked position, and they can separate from one another. This is a really cool lock. Unfortunately, there was a legal battle because of the lifting and the rotating situation and some patents, so they don't really exist anymore. They're at the very least, I don't believe that they're being actively made anymore, but you can still find some of them, and this is just one of my favorite American locks. Because remember what we were just saying about the sidebar versus the shear line, right? We can tackle one problem at a time. We can't do that with this lock. You have to both lift and rotate the pin in order to get that driver pin to set. And that's super hard to do. So, Kaba, who we talked about before, was like, man, what if we made a reversible key? So it's like late and you're drinking and you don't know which way it goes, but it doesn't matter, man, because our key works both ways. They made one of the first ever reversible keys. They'll tell you it was the first ever, but I like to look at patents and I haven't yet. Multi-lock followed them, a bunch of other people followed them, but so now we have a reversible key. So multi-lock's like, oh man, reversible keys are awesome, but what if we put one pin inside another pin? Oh, mess. So dimple locks in general have a problem. If we look at the Kaba again, think about a key blank and a normal pin tumbler lock. When you have a normal pin tumbler key, you have some valleys cut into the key, some peaks, whatever. The possible variations contribute greatly to the security of your lock. The bigger the range of differences in your key, the harder it will be to pick. When you're cutting into the blade, when you're cutting into the flat of the key, the possible distance traveled is very, very small. So the maximum difference in height between the different pins is very shallow. Therefore, these can be what we call raked. They can be raked to death. We go in with sort of a little corrugated piece of metal, and we just rapidly scrub through them, and because the height differences are so minute, they pop open fairly easily to this specific attack. When multi-lock rolls in with their pin-in-pin system, this becomes incredibly difficult. That inner pin is so small, and the way that all of the rakes work is that it will lift both outer and inner pin to the same height. But the outer and the inner pins can actually be at different heights. They accomplish this in the key by milling in two circles, little concentric crater marks into the key. One will lift the interior pin, one will lift the exterior pin, lifting them both up to different heights, and it's super cool. Now, the original multi-lock, Eric Michaud did an awesome attack against it, an overlifting attack. You can look it up. It's called the Michaud attack. But they fixed that, and they iterate faster than almost any other lock company out there. So Linus Yale Jr. and several other people, but I like Linus Yale Jr. quite a bit. He had the revelation. You know, we were talking before about, hey, let's stop having the key act directly on the bolt. Revolutionary. Hey, any access to the tumblers whatsoever is a problem. Let's avoid that with the Lafayette locks. Cool. Linus Yale Jr. comes out, and in painfully flowery language, so I'll simplify it here, he says, any key, any lock that can be opened by a key can be picked. The tentative method was such a powerful force that he finally decided that there was no security through key-based locks. To that end, he and many other people became very interested in combination locks. Now, there are many other routes to get to modern security. One of the big ones that we're leaving unexplored in this talk is China. A lot of awesome stuff is being produced in China. I don't know enough about it yet. Combination locks that have separated wheels, where you operate independently on every wheel in the combination lock, can be easily brute forced, and they can often be easily decoded. In particular, each of these work by having a gap cut out of some portion of the wheel or some other wheel that they're attached to. If you can find that gap, we know that in every combination lock that operates like this, all of those gates in their final position will be in perfect alignment. So, let's quickly open both of these. The sesame lock on the left, we can probe it with a thin piece of metal, or potentially we can even look with a scope to see where these gates are on the inside of the lock. We can see where the gate is on the wheel. align all of those wheels, and then move all of the wheels together, one at a time, trying the shackle, trying the shackle, trying the shackle. Same idea with the one on the right, but if you ever need to open one of these, your best bet is to try to get a thin piece of metal with a 90-degree bend in it in between the wheels. Start trying to turn that small piece of metal. Then rotate the wheel, keep it turned, and when it passes by the gate, all of a sudden, your little piece of metal can actually slip into the gate. Now you know where the gate is. Keep track of that number. Do that to all of the rest of them. Get them all aligned. And all of a sudden, you've taken your 10,000, 100,000 possible combinations and brought it down to 10, or however many letters are around that thing. So, to combat that, because those are easy to brute force into code, we start to see combination locks where the wheels can actually operate on each other. And this is another revolutionary concept. The way that they do this is something called flies. Now, this is really zoomed in and a little bit blurry. What we're looking at is this piece of metal and this piece of metal. I just realized that I was mic'd and I don't need to yell now that I'm back here. Sorry. So, this little piece of metal and this little piece of metal, as you rotate whatever wheel is connected to the dial on the lock, that wheel picks up the next wheel, which then turns and picks up the next wheel with these little bits of metal protruding from either side. This is why when you're dialing the lock on your locker or you're dialing the lock on your safe, you have to move however many times in this direction, and then one fewer times in this direction. What you're doing each time is leaving a wheel behind that's positioned. And then you go back in the opposite direction. You pick up however many wheels you need to. You leave the next wheel behind, and so on and so forth. And this is how you get them all aligned. Really difficult to brute force. So much more difficult to brute force. They make auto dialers for safe locks. You should expect them to take days. They'll get it open. However, the first of these new combination locks had basically a sidebar. We call it a fence. It's a big bar of metal that's going to fall into the gates in the wheels. When that was acting directly on the wheels, it was really easy to feel, especially if the action of that bar was controlled by an arm that you had to pull or something like that to force into it. You could just pull that, apply that force, and feel everything that's going on. Cool. So, they invented what's called the nose. The nose is this little bit right here. Now, the nose is connected to the fence. The fence runs over the top of all of the tumblers in the lock. The nose is riding on this wheel back here, this smaller wheel, and that's called the cam wheel. The cam wheel is actually the one that you're controlling when you're dialing the dial. There's a post running all the way through to it, and that's the one that you're manipulating. As the cam wheel turns, you pick up another wheel, you pick up another wheel, but most of the time, the nose is held up, and therefore the fence is floating above and not actually touching any of the wheels in your safe. So, this was a huge innovation, really, really cool, until the micrometer attack was invented. The way that this works, we're actually going to step back to the fly real quick, because the way that this works is very cool. If you think about the gate on the cam wheel, kind of like a funnel, imagine sticking your finger into a funnel, and then go back and forth. Now go a little bit deeper. You're traveling a shorter distance, right? Same deal with the fly. That, by the way, is not at all my analogy. I may have read it in Matt Blaze's Safe Cracking for Computer Scientists, which is an amazing paper. What you're going to do is take all of the wheels in the safe, turn them, and park all of them at some number. We'll say we're going to park everything at 40 right. We're then going to turn our cam wheel with the dial back around until we feel that nose click into place. Because the nose will dip down as it approaches its gate. And if you can measure where you first hear the nose touch the gate, and then where you next hear the nose touch the gate, or feel it, you know how far the fence has descended. you're then going to go back through and move all of your wheels 2.5 positions. You're going to go back to wherever you found the fly the first time, still free of all of the other wheels, just turning the cam wheel. You're going to measure it again, and measure it again, and measure it again, and keep repeating that process. You're going to break all of the numbers on the wheel up into smaller parts. You're going to graph out all of your measurements. And for the most part, you'll have 2 steady lines, because the fence is being held up by all of the wheels at once, and the nose can't descend too far. But every once in a while, you're going to see a little dip into the funnel. What's happening is that one of the gates is aligned underneath the fence. And you've just discovered that by seeing how far the fly descends into its gate. Every time you see them narrow, you know that their fence is laying on a gate, because it can go down just the tiniest bit more than if every tumbler was round underneath it. This takes a long time. It takes a lot of patience, and it takes a really delicate touch. But it's incredibly powerful. This is the tentative method of safe cracking, really. That's not the best illusion, but it is that powerful. So they came up with a couple of different ways to defeat this. Number 1, put in some oblong wheels. So with all of your circular wheels, everything will be fine, but you pop in an oblong wheel or two that are just a little bit bowed out, and now the chances of your oblong wheel lifting the fence up a little bit too high so that you can't actually feel where a gate is, and lifting the nose a little bit higher and giving you the reverse reading, going higher in the funnel, increase, and it very much obfuscates the process and makes it much more difficult. Very simple change. A couple of companies just put in a little détente, little ball bearing on a spring that just rattles on the back of the cam wheel. The cam wheel is serrated, and every time you turn it, you hear a and that feeling of it clicking and the sound of it clicking makes it very difficult for the much more minute. But then Sargent came out with the magnetic fence, and this thing is super cool. It still has a fly, but instead of relying solely on the fly riding along the cam wheel, the whole operation is actually held up by a magnet. And then once every rotation, it's separated and kicked down to tempt if the combination is there yet. So the gross majority of the time that you're rotating, the fence and the nose aren't touching anything at all. It's just every time you clear the magnet, and then the magnet picks back up again, and it becomes incredibly difficult to encode anything. At the time, at the very least, it was said to completely defeat the micrometer attack. But there's also the vibratory attack. The way that the vibratory attack works is that because the wheels in your safe have a big gap cut out of them to accept the fence, one part of your safe has less material than the rest. So if you can put a palm sander up against it, or if you have a big naval ship that you have a bunch of safes on, this is the potentially apocryphal story that you always hear, is that there were ghosts on the Navy ship opening up safes, and it turned out that just the vibration of the ship at sea was allowing all of the wheels to settle out so that the fence could fall right in at the top when they were all aligned. So really easy fix to that. Just go ahead and remove some material from other parts of your wheels. This actually is balanced to some degree, or at least it's changed the balance. But they're also done like this in order to rekey them, which is not something we'll get into right now. But that's how you solve that problem. So again, everybody always wants to mess with the form factor of these things. So what if we can add a lot more wheels and make it really tiny? Well, John and Bob Laughlin did that with their RoboKey cylinder. So the RoboKey was meant to be a lock for ships at sea. Wanted a strong mechanical lock that could bear up to the elements, but it was going to be dialed with a robo-dialer that was just a stepper motor getting instructions for right and then left and so on and so forth. But this had 7 to 11 individual wheels, and it had this tiny little emergency dialer where if your robo-dialer wasn't working, somebody could tell you the 11 number, and you'd have to turn 11 times in this direction, and then 10 times, and then it takes forever. Very cool lock, though. Okay. What if we make it tiny, we add a bunch of disks, and then we bring a key back into the mix? Really cool idea, right? So Abloy did this back in the very early 1900s, 1900-something, created the first, at least mass-produced destainer lock. There's some people that have done some great scholarship that says that maybe the Germans had it first, but Abloy are definitely the dominant brand. So of course we added the key back in, right? So we now have the tentative method. This chased these guys for like 80 years, but they kept making new versions of the Abloy. But then they solved it. And people often ask me, are there any unpickable locks on the market? And the two that I can say are the EVA MCS, which is a long line of thinking about magnets, which I can't cover in the 50 minutes that we're doing this. And the other is the Abloy ProTech. Nowadays I have to say it's the Abloy ProTech 2, because the Abloy ProTech 1 has probably been opened, but nobody's told me how, but I heard that it wasn't the tentative method. Anyway, how they solved this was that they separated the act of applying pressure to the act of manipulating the individual tumblers. So, the moment that you apply pressure to the tumblers, you cease being able to turn them. So you can turn them and then try, and turn them and then try. You could build some tiny machine to potentially brute force this, but you can't feel how the tumblers interact with their sidebar. You can't feel that relationship. And that's what the tentative method is all about, the relationship between the tumblers and whatever it is they're blocking. With that gone, tentative method was defeated, at least for then. And in the ProTech 2, as I understand it, it's still defeated. But I'm very curious to find out what happened about the ProTech 1 if anybody wants to tell me on YouTube. Okay, so the other big complaint that has kind of chased people throughout history is how easy it is to duplicate keys. This has become a much more interesting conversation since the first person patented a key. They protected their key from being duplicated by any generic manufacturer by patenting the actual blank and being the sole distributor of it. And this was offered as a safety feature. There are a lot of key-based attacks where if somebody has a blank to your lock, they can do a lot of things to it in order to open it up. By patenting it, they can no longer do that. Schlegg Primus, in their marketing literature, says that this key is protected by 4 utility and 2 design patents, so nobody can create generic blanks for it. So that's all well and good until the Supreme Court in California came along and said, oh no, generic manufacturers, you go right ahead. That shouldn't be patentable. Everything's fine. You make it. Nobody cares. And that caused a big kerfuffle, and we're still waiting for some more of those battles to take place internationally, but there are a few firms getting out ahead of it. CES is a big one of them. They advertise quite boldly that their locks are not protected by patents, their keys rather, they're protected by trademarks. Because the profiles of the key are a logo for them. So if you try to reproduce their logo in metal, you are infringing on their trademark. Very clever, and it's yet to come to any sort of court. Nobody's tried it out yet, but there's one that I was looking for that Han Fei showed me, I believe, that just says CES clearly in the metal of the wording of the key. But then the French Patent Office comes along and says, screw all this noise, you can't protect your keys at all unless you have a movable element in them. If you're just bringing us bare metal, we're not going to issue you a patent, you can't protect your key. So, Multilock, Dom, a ton of Abloy companies, a lot of other people come out with these little floating elements. And they're actually kind of clever because as they insert into the lock, they're going to like duck down under a little protrusion and then pop back up because of little dudes inside of the lock that are forcing them beyond the scope of the actual blank. And it turns out to actually be a pretty cool deal that the French Patent Office did this as far as moving the technology forward is concerned, because you can reproduce any bare metal blank. Try impressioning this. Try creating a photo duplicate of this. Crazy hard, right? Okay, so that's all well and good. So how are people going to get around this? Well, the French Patent Office said this, and Fichet, one of the most important French patent companies, French lock companies, said, screw it, we're not putting a movable element in our key. We're going to patent it as part of the assembly process. The way that the Fichet 3D works deserves a talk all on its own, but I'm going to try to take you through it real quick. Each of these gears, and there are 2 here, 2 here, 2 here, 2 here, and so on, have a triangular piece inside of them. The crazy-looking key moves through the triangle, rotating it into different positions. As it rotates the gears act on these sidebar wafers. The sidebar wafers have little serrations that fit into the gear, and they're dragged along in a channel, and they have a gate. As they're dragged along in the channel, that gate is drawn back and forth, and when all of the gates are aligned, a sidebar on either side will be able to drop into place. It's a really, really, really cool lock. However, all of the components inside of it are exactly the same as one another. Every gear is the same as every other gear. Every triangular bit is the same as every triangular bit. Every sidebar wafer has its gate in exactly the same place. The way they build the difference in is that they slide the key into the lock and then put the sidebar wafers on, so that whatever position all of the gears are in, with the key inserted, is the open position of the lock. They then slap the sidebars in, remove the key for the first time, and everything is scrambled to the now unlocked position. And as a result of that assembly process, they were able to patent protect their key, making an end run around the French patent office. I only have a minute or so here. I know that this wasn't as quick and definitely not as funny as my other talks here at RVAsec. But I wanted to give you a glimpse into the amazing history of security engineering. People say to me all the time, and one of you might be in the audience, and I feel bad because I yelled at you in one sentence. But people come up to me all the time and say, locks only keep honest people honest. And to me, that just throws out 4,000 years of security engineering. The work that these people are doing is pure mechanical genius. And as cool as it is to get the concept, and as cool as it is to figure out how to open a lock, the people that can hold something like this together in their minds before it's ever existed in the world are brilliant. I hope that through this, you have a little more sense of what goes on in every lock that you handle, and what its long history is, and the fact that locks of every different form somehow always relate back to one another, and somehow always relate back to people that were in complex societies that needed security just like you and I did thousands of years ago. Security goes deep. I have a lot of people to thank for this. The bottom part there, where the various photographs came from in particular. A lot of great places. Additionally, many of the photographs came from the Yale and Towne collection that's currently held by the Stanford Museum. This is one of the big projects I'm working on right now. It is a lost collection of hundreds of locks collected by the Yale and Towne Company over the course of 100 years. And we found 2 parts of it. We're still looking for the 3rd part of it. We're trying to bring them all back into the public and re-exhibit them. And I want to thank directly Peter Field, who is just a lion in his field. He's the director of research at Medico, and I have watched him give, I think, 15 hours of this talk. And it's amazing. The other battles that we're not covering right now, the tiny little wars taking place in small cities where one lock is made just there and never leaves that town to solve one problem, an anthropologist's dream. And Peter Field knows all of it and shares it. Han Fei is amazing. He first excited me about the mechanics of locks, and he still produces a ton of incredible white papers, and I owe a huge debt of gratitude to him. And finally, Matt Duplessis is actually an old boss of mine who taught me to love mechanical engineering before I ever knew a thing about locks. Thank you to all of them. Thank you so much to all of you. I hope you learned a stupid amount. Thank you. Thanks, man.